So this is the last thing that we're going to talk about with respect to lipid metabolism, and that is cholesterol. Cholesterol is a kind of, well, cholesterol is an example of a lipid. It's kind of not really what we look at when we talk about other lipids, because when we're talking about other lipids, we're talking about like triacylglycerols and fatty acids and fatty acyl CoAs and everything like that. But cholesterol is an example of a lipid, and one of the things that, or its primary function, is that it modulates membrane fluidity. So a higher concentration of cholesterol is going to make membranes generally a bit more rigid. Cholesterol is also a precursor for bile, as well as some steroid hormones, particularly sex hormones, and it is also involved in the formation of atherosclerotic plaques, which can lead to heart attacks and strokes. So cholesterol is something that you probably should know about. Now, the biosynthesis of cholesterol, it has some similarities to it has similarities to ketone bodies. First of all, cholesterol is going to be synthesized starting from acetyl-CoA. Acetyl-CoA is going to be combined to ultimately make hydroxymethylgluteryl-CoA, or HMG-CoA. That HMG-CoA is going to be used to make isoprene units. These are two examples of isoprene units. Actually, this is identical. These are both isoprene units. The difference between them is the placement of that double bond. These isoprene units are 1, 2, 3, 4, 5 carbon structures with 2 phosphates. This would be an example of IPP, isoprene diphosphate. These isoprene units are used to ultimately go on to make cholesterol, as well as different pigment molecules and vitamins. Carotenoids are examples of molecules that are synthesized from isoprene units, and so these are examples of pigment molecules. Ubiquinone is an example of an electron carrier. And then there are certain hormones that can be synthesized from isoprene units as well. This that my head is blocking at the moment, this coenzyme Q is, well, we talked about coenzyme Q in terms of the electron transport chain that has an isoprene unit affixed to it. Okay, so the first step in cholesterol biosynthesis is basically the exact same as that of ketone body synthesis. The difference is that this is done in the cytoplasm rather than in the mitochondria, where our ketone body biosynthesis takes place. So in order to do this, you have to have your 2 acetyl-CoA molecules. You have to have a thiolase enzyme. That thiolase enzyme is going to remove the coenzyme A from one of your acetyl-CoA molecules. I'll just draw my star by the molecule that's removing that coenzyme A from. Those 2 carbons are going to be transferred onto this end right here of my acetyl-CoA molecule, and I'll end up with acetyl-CoA. Now this right here is the molecule that results, or is basically identical to that of ketone body biosynthesis. So this actually is a ketone body, or that acetyl-CoA is a ketone body. Now, the second step is also the same. So this enzyme right here, an HMG-CoA synthase, that enzyme is going to add 2 more carbons from another acetyl-CoA onto this carbon right here of our acetyl-CoA, and we're going to end up with we're going to end up with our beta-hydroxy beta-methylgluteryl-CoA, or our HMG-CoA. And one thing that I'd like you to remember is that it's this carbon right here that is the one that ends up forming a carbon-carbon bond with this carbon right here. So this CO2 that we have is this carbonyl oxygen. We use water to break that bond, releasing our coenzyme A and giving us our HMG-CoA. So this is identical to that of our ketone body biosynthesis, but our stopping point, or kind of our diversion, is whenever we have this HMG-CoA. Then we're going to go on to begin isoprenoid or isoprene biosynthesis. Okay, so in order to do that, we have this enzyme HMG-CoA reductase. Now, HMG-CoA reductase, what it is going to do is it's going to use NADPH, 2 molecules of NADPH, and we are going to be replacing this carbonyl oxygen with a pair of hydrogens, and we're going to have to remove this coenzyme A in order to put an OH on there. And so what we're going to be doing is we're basically going to be putting 2 hydrogens onto this carbon right here, and then we're going to throw an OH, or this oxygen becomes an OH out here. And that's going to be the formation of our molecule known as mevalonate. So HMG-CoA reductase, that is our first committed step toward isoprene unit synthesis. Now, these isoprene unit synthesis can go in a number of different directions. It can go to vitamin biosynthesis, but when you think about kind of the risks associated with where this is going to be going, this says isoprene unit synthesis. This does not say cholesterol biosynthesis, but the likelihood that this molecule or these carbons end up in a cholesterol molecule is fairly high. And so as a result, this enzyme, HMG-CoA reductase, is a target for many different cholesterol-lowering drugs, so that you can actually regulate and inhibit the amount of, or reduce the amount of cholesterol that is synthesized in vivo. All right, well, I hope this is helpful. We'll continue on in the next video. Thank you very much. Have a good one.